Welcome to AP Chemistry at Hanani High School. I'm Brian Brown, and today we'll be looking at section 21.4, which gets into the concept of half-lives and contains one of our main math ideas for chapter 21. Now, the rates of decay of nuclei. So we talked yesterday about unstable nuclei. So some substances, because of too many protons, too many neutrons, too large of a nucleus, are unstable, and they will undergo nuclear reactions to achieve stability through a variety of different decay processes, alpha decay, beta decay, and so on. And those are the primary two. Well, the rates of decay of nuclei are very predictable properties. They occur at a very set rate for different types of isotopes. And to make the math a little bit easier, one of the ways in which we often talk about rates of decays of radioactive substances or unstable nuclei is to use the concept of half-life. It's the time required for half of the sample to react or decay. And we're dealing with radioactive decays. It's actually what's known as a first-order decay. So in this particular type of decay, the half-life is stable and it's independent of the amount of that you start with. So regardless of how much you start with, it's going to decay at a constant rate. So a half-life is literally the length of time it takes for half of it to disappear. So if you had 100 grams after one half-life, you would be down to 50 grams. And after another half-life, you'd be at half of that, so you'd be at 25, and so on. So a half-life is a relatively simple way to look at radioactive decay type reactions. So one type or one mathematical method of talking about decay is to use the concept of half-lives. So how much cesium-137 will remain after 3 half-lives? So in this particular case, we're not really talking about a length of time. They don't tell us how long a half-life really is. They just say it goes through 3 half-lives, how much is going to be left. Well, you really have to do, because this would be true for anything, regardless of what substance it was. So this could be uranium-235 as well as cesium-137. The difference would be what is the actual length of time that would take. But the concept of how much will be left after 3 half-lives is always going to be the same. After 1 half-life, you're going to have 50% left. After 2 half-lives, you're going to have 25% left. And after 3 half-lives, you're going to have 12.5% left. So it doesn't really matter what the type of reaction or type of nuclei is. The concept of half-life is the same in all situations. And one simple type of math problem related to this is literally divide by 2's. How many times do I have to divide by 2? So if 25% of my sample is left, how many half-lives did I go through? Well, I started 100%. After one half-life, it's 50. After another half-life, it's 25. I went through 2 half-lives. And if you knew the length of time of half-life was 1,000 years, that would mean that that sample was 2,000 years old. So simple division by 2 is often a useful way to look at more simplistic radioactive decay type problems. For more complex problems, if it's not exactly a nice round divide by 2 situation, we have an equation that can handle pretty much every other situation, including the simplistic ones. But when you read a question, if it's as simple as how many times they have to divide by 2, that's all you need to do. You don't need to go through any complex math. Now, as I'd mentioned earlier, radioactive decay is what is known as a first-order decay process, first-order kinetics. Now, this is something we'll actually be talking about in Chapter 14. So what we're actually practicing here with radioactive unstable nuclei is going to give us a little background for when we come back to this in Chapter 14 later in the year. Now, here is the equation for first-order decay processes. Now, that's not the way this is going to appear on the AP test. So this is the form that appears on the AP constant sheet. So this is the form that I'm usually going to look at. These two things mean the exact same thing. They're mathematically identical to each other. So they're identical. The difference is this is what is often mentioned in the book, but that's not the equation as it's represented on the AP constant sheet. So this is the form over here that I strongly recommend you get used to using, because when you take the test, when you take the AP test, that's the form of the equation you're going to see. So you might as well get used to handling it and get comfortable with it. Now, what do the things stand for? Well, N sub O or A sub O stand for the initial number. So, how many particles we actually have at the start, which could also be the initial mass of nuclei at time 0. So the naught literally means at time 0, how much do we have? And at T would be at some time later. So what is the mass now at of that substance? So we started with 58 grams of cesium-137, and now we only have 42 grams of cesium-137 because it's decayed into other things, and that's how much of my sample's left. So the naught, the zero, is at time zero, so at the beginning, and then the t is at some time later. Now, one of the things I didn't put in the notes here, but you're going to see this in a problem later, is we can also look at this as um, the amount of decay that's occurring. Because when you've got a larger sample, it's going to be decaying faster, simply because there are more particles there to actually decay. So if you were to put a Geiger counter next to a large sample of some radioactive substance, at the beginning, it's going to be decaying. More particles are going to be actually decaying at that point because you got a larger sample size. So when you've got a big mass, half of it's going to be a larger number. So we can also substitute into these spots the actual number of particles decaying per unit of time at time zero at the beginning and later at time t. And a lot of times you'll be seeing this as written as disintegrations because it's literally what's happening is it's undergoing a nuclear decay. It's disintegrating and throwing out alpha beta particles that we can detect. So how many particles per second or per minute is it throwing out now? That can be substituted in for A naught, and then at some time later that can be substituted in for AT. So usually you're seeing the number of particles, the mass of the particles, or the number of decays or disintegrations at the beginning and later. Now, at half-life, so remember the concept of half-life is how long it takes for half of it to disappear. At T half-life, it would be true that we would have half as much as what we started with. So if we were looking at a half-life situation, so this was what we call T1 half, if that's the time is here, the actual time of a half-life, then whatever we started with N sub O, we are going to have half of it left at time T. So we can actually substitute that into that top equation and solve, and what we get is this equation down here on the bottom, which nicely enough is now on the AP constant sheet. Previous years I've mentioned this is a really useful equation you got to memorize or solve from the top equation, because if you literally plug in that 0.5 n sub o into that top equation and solve, you get this bottom equation. So it's not that hard to do it. You just plug in the numbers. You could say I had 2 and now I have 1, solve for it, and you get exactly what you see down here. That's really where that 0.693 comes from. But since this is on the equation sheet now, you don't really need to worry about memorizing it. So the k in this equation is our rate constant. So it is a constant that's going to be different for different types of substances. So it's a characteristic property of a substance. So if we know how long the half-life is, we can solve for k using this equation. If we know what k is, we can solve for what the half-life is. And this equation is a useful equation, and it's now on the AP constant sheet. So you've got two forms of equations on the AP constant sheet that are going to be useful for the type of math we're looking at here with radioactive decay. So if you know the half-life, so we know that it takes 1,000 years for it to decay, we can plug that in and we can calculate the rate constant or decay constant K. So by substituting the amount of a radioactive nuclide present at a given point in time with the amount normally present, one can then follow and use the following equation to find the age of an object. So in the equation, if we know what K equals, because we know what the half-life is for that substance, we could then solve for K, plug that into this bottom equation, and we can find out how old a sample is. So if we know how many we had at one point, 12 grams here, and we know after a certain amount of time, we no longer have 12 grams, we're down to 2 grams. We can actually calculate, if we know what the half-life is, we can calculate what the time it would take for that to happen. But we have to either know K or we have to know the half-life, and then we can use that to solve K. And that's what you'll see in a typical problem. If they tell you the half-life in the problem, get used to the fact that pretty much 100% of the time, the reason they're telling you it is so that you can find K. So you're going to plug that half-life into that equation and solve for K. And remember, this equation is on the AP constant sheet. So you just need to know, oh, when they're telling me half-life, that means I can solve for K. And then I can use my first order decay reaction to solve for time or AT or A naught or whatever it is that they ask me to find in a particular problem. Now, be careful of this one. In the same part of the AP constant sheet where you're going to find those two equations, you're going to see this equation. Never, ever, ever, ever use this equation for anything from chapter 21. This is actually our second order kinetics reaction equation. So all nuclear reactions are first order. This is not appropriate if we're dealing with nuclear decay then. So you'll see that on there. It has some of the same symbols that we had for the other equation, but don't touch it. Yes, when we get into chapter 14, we'll be doing some second order stuff. Then you'll need that equation. But for right now, chapter 21, make sure you never do anything with that equation. Okay, here's a typical half-life problem. So this is one of many types of questions you can do with this, and you'll try some in your homework. A wooden object from an archaeological site is subjected to radiocarbon dating. The activity of the sample that is due to the amount of C14, which is a type of carbon that is radioactive, is measured to be 11.6 disintegrations per second. So this is an example of what I said earlier with that equation. You know, that you can look at it as the number of particles, you can look at it as the mass of the particles, or you can look at it as how fast it's decaying at this point, which is measured in disintegrations per time. So at this point, its disintegrations per second would be 11.6. Now, the activity of carbon-14 for a sample of equal mass with fresh wood is 15.2. So if we had this same sample cut fresh from a tree, we would see that it would be disintegrating at 15.2 disintegrations per second. So we know it's older than that because it has already decayed some, and now we don't have as much left, so its number of disintegrations per second is less. Now, the half-life of carbon-14 is 5,715 years. Remember, a second ago I pointed this out. Whenever they give you this, what that means is you can find K, which is something we definitely need for this problem. So what is the age of the archaeological sample? So first, we're going to use that equation, this one, and we're going to rearrange that to solve for K. So we plug in for T1 half, 5,715 years, and we now know the decay constant for this particular substance, carbon-14, is 1.21 times 10 to the negative fourth decays per year. So that would be our unit. So we now have our K, and we can now plug that in to this equation. So they gave us how many disintegrations we're at now. They gave us how many disintegrations we would originally be at, and we just solved for K. So we now have an equation with one unknown, which is T. We can plug in and solve for T. And in this particular case, we'd see the sample was 2,230 years old. And this is something that is a very common application when you have organic matter to determine how old it is from some archaeological dig. So what we can basically say is the piece of wood as a tree existed 2,230 years ago. And at that point, the tree died, it was cut down, and it was made into this artifact. So as a rough guess, we could say that the object is going to be about 2,230 years old. And remember, decays are constant. Can't change them with temperature, can't mess with them with anything else. The half-life of radioactive substance is immutable. So it's going to decay at that process, and there's nothing we can do to change it. Now, one other thing I want to point out here, because otherwise you're just using that equation to solve for different things. We could solve for, let me jump back here real quick. From this one equation, we have four unknowns potential. So four variables. We can solve for any of the four. So remember, I just showed you a problem of how we would solve for T. That means we need to know this one, and that one. But we can actually solve for any of these. Sometimes the problem they may ask you, what was the decay constant? Sometimes in a problem, they may ask us what was the size of the original sample, or they may ask us how much is going to be left after this length of time. So really, we have three different things here they're usually asking us, but it is possible they could ask us that as well. So we kind of have four things that they could ask, but usually they're going to tell us the half-life so we can solve for K, and then we can do problems where we solve for any of these three. We just looked at an equation where you would solve for T, but remember, you can solve for any of these situations. Oh, and mathematically, one thing to point out here, if you have the ln of A at time T that we solve for, and we find that equals some number, making something up here too, that's the natural log of what we want. This doesn't mean AT equals 2. This means the natural log of AT equals 2. Remember algebraically, how do we get rid of natural log? Well, that's where the E key comes in. So E to the ln of A is going to reduce to AT, and that's going to equal E to the second. So in your calculator, you would use the e to the 2 key. So remember, if you want to get rid of the natural log to find out what AT is, then you're going to be using the e key. If we had logs, then we'd be using the 10 to the x key. But if we've got natural logs, then we're using the e key on your calculator. So if they ask us to solve for either of these two, remember, when we solve for it, what we're actually solving for is the natural log of the answer we want. E to that would get rid of the natural log component, and we can solve for it. So be aware of that algebraically. Now, finally, if you know how much mass changes, so let's say we had a situation where we had 0.750 grams of cobalt 60, and over time it decayed, and now we have left 0.500 grams of cobalt 60. So let's say that's the particular situation we're looking at. And the question is, how many particles actually decayed? Well, if we know the mass difference, we can convert mass to moles, and we can use Avogadro's number to convert moles of atoms, and we can actually determine how many atoms decayed. And that's the algebra you're seeing here. So if you want to know, based on a mass change, how many particles decayed, or how many alpha particles were created, or whatever, realize for every atom that decays, you get one alpha emission or one beta emission. So if we can determine how many atoms decayed, then we would know how many beta particles were released or how many alpha particles were released depending on the type of emission. And remember, it's just straightforward dimensional analysis. We've got grams, we can convert from grams to moles, and we can convert from moles to atoms. And if we know how many grams decayed or dropped, then in this particular sample, it would be 0.250 grams were what decayed. Well, that means it was 2.5 times 10 to the 21st atoms, which would mean when every one of those atoms decayed, one beta particle came out. So if they're asking you to do this type of thing, it's not actually using that original equation. It's a different type of math. And remember, we can convert from mass to moles and from moles to atoms. And for every atom that decayed, that means we had a alpha or beta particle released. And that ends our second set of notes over the chapter.